Ariel. Take it away.
Right. So in this paper, we're focusing on parallelizing dynamic languages, specifically built-in collections. Synchronizing built-in collections is sort of the next step for us in parallelizing dynamic languages after solving parallelizing objects. Dynamic languages tend to have a few built-in collections like array hash, array plays multiple roles like a list, like a queue, versus static languages where you would find large libraries that contain a lot of different implementations of structures. We would like built-in collections to be, in order to make them parallel, we would like them to be concurrent, we would like them to be thread safe and scalable. So that's how we get the parallelization. But there's one more thing that we would like to have, which is we would like to maintain single-threaded performance because the ecosystem for dynamic languages is mostly written for single-threaded. And so we'd like to keep that performance without losing, basically without paying any penalty for the synchronization overhead for code that was written for single-threaded. So in our work, we're basically achieving all of these. I don't know why the feedback. Why is synchronizing it? So first of all, some work has already been done to parallelize dynamic languages. There is the global interpreter lock, which is basically lock the entire VM on every action. So essentially, this will like the one ring that rules them all. Is anyone familiar with that? So we get sort of concurrency, thread safety, but we don't get any scalability out of that. So that doesn't really help us. There's been some work with using transactional memory approaches, which give us most of this, but a lot of times they introduce single-threaded overhead, and also the scalability is not as great as we would like it to have, because of the overheads. So, for example, think of embarrassingly parallel benchmarks where we wouldn't expect any overhead because of no contention, but the transactional memory approach will add some contention on that. And there's other approaches like locking every access to a collection. So again, no scalability. And believe it or not, there are some VMs that just do no synchronization. Meaning, so yeah, we get scalability, but no thread safety. So it's essentially like walking a tightrope without a safety net, right? So why is it so difficult? Why is it so difficult to parallelize built-in collections in dynamic languages? Well, imagine two threads trying to append to an array. Array, I said, the array doubles as a list, queue, whatever. So these are very dynamic structures. And if two threads are trying to append to it, well, we have a couple of possible outputs. First of all, if we have the GIL, the global interpreter lock, then it will be completely sequentialized. Everything will work correctly. But again, we'll pay for it later. If we don't have the GIL, if we remove the thread safety requirement, then we can run into some concurrency errors from VM errors and other things that the user would not expect to get when they run their code. Or we could get some lost updates. So for example, let's say we have two threads. One of them is updating the array and another is appending to the array. So here's our little array, and we have one of them updating, one of them is appending to the array. And what happens is that whether we get 8 or 3 at the result depends on when the copy actually happened, right? So we can run into a situation where we lose the update. So you could say, yeah, you could cast or you could do other stuff, but that adds synchronization overhead. So we want to avoid that, right? Another challenge is the storage strategies. Now, storage strategies is an optimization that basically defines for collections how to behave in certain scenarios. So for example, if we store only integers into an array, a storage strategy could say, well, store it as an int array, right? Because we only use integer values in there. And it will work faster than, say, an array of pointers into objects and all of that. However, as soon as we store a string into the array, because dynamic languages are typeless and they allow that, we will have to convert the array into an array of objects, right? In order to be able to accommodate the polymorphism. Now, these transitions are done implicitly in the VM, and we have similar concurrency issues as before, right? Okay, so our approach is called concurrent strategies. Again, with the strategies, so these strategies actually define to the collections how to synchronize themselves based on the scenario, similar to the concept of storage strategies. So what do? Essentially, we split the heap between the local and shared objects. We do this by tracking local versus shared. We'll show it pretty soon. We also do gradual synchronization. So essentially, imagine having strategies that gradually apply more and more synchronization overhead based on how the objects are used. We will present strategies for array and strategies for hash, which are the main kind of building collections in Ruby that we dealt with. So tracking local versus shared. So every object in most dynamic language implementations today also has a shape, which is like some implementations called it a hidden class, some implementations call it differently, but it's a structure that defines how the object looks like, meaning where the fields are, what the size is, if it's an array, what the types and so on. And we add to that, to the shape, another flag which says whether it's shared or local. So obviously a shared object will be in what we call our shared part of the heap. So imagine a thread that creates some objects, and it has a bunch of, so all these objects are going to be in the local part of the heap, right, as far as the thread is concerned. But as soon as we try to assign that local object into a shared object, there is a write barrier that applies only to shared objects that will trigger and will start scanning all these objects and slowly converting them, not slowly, hopefully, converting them to their shared shapes. And eventually, all these objects will join the shared part of the heap. This is kind of like GC mark, if you're familiar with the algorithm. Let's see some strategies for, say, Ruby array. So first of all, we have what we call the local strategy. Local strategy is basically when the array is reachable by a single thread, no synchronization. Because no sharing, no synchronization, no need. We have something we call the fixed storage strategy, which is a strategy that assumes that the array size and storage will not change. So there are no triggers that will change it. As long as we can keep within these assumptions, we can stay within this strategy. And we have a dynamic storage strategy, which is a shared dynamic, sorry, this guy decided to jump further. We have a shared dynamic storage strategy, which allows unrestricted use on the one hand, but it also applies full synchronization. So we have basically no synchronization, minimal synchronization, and full synchronization. You see the gradual part that I was talking about, right? So how do the triggers look like? So upon sharing, obviously, we will move from a local to a shared strategy. So we switch from a local to the shared fixed storage. And if our assumptions about the behavior of shared fixed are violated, we will switch to the dynamic storage. Now, keep in mind that if we switch from a local to a shared, the collection is still local, so we can do the switch safely and before we actually make it shared. However, once it's shared, we need to switch to the dynamic one, but it's already shared, right? It's already out there. So we need to do something in order to, we don't know who's accessing it, who's using it, so we need to make sure it's, so we use guest language safe point, which is a form of barrier or stop the world kind of approach. We just wait for things to relax a little bit, and then we switch to the dynamic storage. And that's how we provide the thread safety for array. So the shared fixed storage applies no synchronization for read and write accesses, and it does runtime checks for size and storage strategy changes. The dynamic one, as I said, as I mentioned, we transitioned to it via the guest language safe point or the stop the world kind of barriers. All accesses are synchronized. We get concurrent and scalable writes, and we get serialized storage strategy changes. And this is provided by a new lightweight deadlock that provides a synchronization element for this strategy. Let's take a look at the hash. So the hash in Ruby is implemented as a bucket array, like a regular hash with a dangling list of elements. But it also contains a doubly linked list that maintains the insertion order. That's part of the Ruby specification for hashes. So as long as it's reachable by a single thread, we don't have to worry about it. But as soon as we switch to the shared, we switch to a concurrent bucket strategy, where we use a lock-free singly linked list for the buckets themselves, a lock-free doubly linked list for the insertion order, and a lightweight lock for the bucket, the bucket array itself in terms of resize. And that's how we provide thread safety for the hash. The full synchronization that I mentioned before is achieved by using the lightweight layout lock. So what is a layout lock in general? So a layout lock is a locking mechanism or paradigm that extinguishes between three participants. We have a reader, which can read the data, obviously, a writer, which can modify the data, element anywhere, and then we have a layout changer. Now, the layout changer is a special player in the game here, because it assumes that it has exclusive access to the data structure, meaning it can basically do anything in it. Move things about, resize, do whatever it wants, and that's the layout changer. Now, readers are scalable, writers are scalable because there's no potential between them, but the layout lock paradigm assumes that layout changers are infrequent. But for our case, this doesn't apply because we can have, say, sequences of appends or other stuff that if this is too heavy, it will not work. It will not scale well or not work well. So let's take a look at how the lightweight layout lock kind of works. It basically is based on a shared exclusive lock, which could be any kind of reader-writer lock or whatever. It doesn't have to be super scalable or anything, just a shared exclusive access. It has a rescan flag and a list of thread states. A thread state basically includes 2 bits, whether a thread is writing or a layout change is active, and it's maintained by the thread itself. Threads can register dynamically with the lock. Now, the implementation of the lightweight layout lock distinguishes between a fast path and a slow path, where reads in the fast path essentially just access the data structure. They don't do anything other than just read, in this case, for example. Writes actually have the responsibility of turning on those W bits that you can see here, the writing bits, because they have to notify potential layout changes that they're writing. And, but of course, writes and reads can be concurrent. And however, a first layout change after a read and write operation will fall into the slow path because it will have to do a lot of stuff, and I'm going to take a deep breath and go through the process. So what it does essentially is it will lock the base lock in exclusive mode, basically has the data structure. Then it will go and trigger and mark all those L bits and then turn off the rescan flag, meaning I scanned all the thread states, I turned all the L bits, so I can turn off the rescan flag. Up to here. After everything is set, then we can proceed and do the layout change. All right? Now, and then we can release the base lock and go ahead. Now, if we have a layout change after a layout change, now all the L bits are already turned on, right? And we have that rescan flag, so we'll take advantage of it. So if T3 wants to do a layout change now, all it has to do is lock the base lock, check the rescan flag. Oh, it's all turned on. That's fine. So just go ahead and do the layout change, right? So, and we're done. Now, read and write that happened, first read and write that happened immediately after a layout change, will need to recover because, as you can notice, those L bits are still on, right? So a reader will have to, in this case, go and check and see, oh, the L bit is still on. So that's where the shared part of the base lock comes in. The reader will have to capture the lock in shared mode. Now, the reason it's shared is because multiple readers and writers can wake up after a layout change and will want to change their state. So they all have to capture that lock together. So that's why it's a shared lock. So it will capture the shared lock and turn on the rescan flag to notify any potential layout changes that, you know what, one of those L bits is off, so we'll have to do some work next time. And then it will go and proceed with the read, and it's basically done in that stage. In terms of our evaluation, so there are a lot of details in terms of, we actually, in the paper, we actually offer, one of the other contributions in this paper is the whole suite of benchmarks for dynamic languages. So we tested on a whole lot of things, but I'm just going to go over a few because of the lack of time. And we tested up to 44 CPUs in some benchmarks and so on. Well, just let's go ahead with the benchmarks themselves. So the first thing we did is verify the single-threaded performance claim, right? So we took a bunch of benchmarks and we measured them with Truffle Ruby, which is the Ruby implementation that we used, and Truffle Ruby with Concurrent Strategies, with our implementation in there. And as you can see from the box plot, and the performance between the two executions is almost identical. Even the outliers in this run are pretty much in the same places. So, and again, the reason for that is because we distinguish between the shared heap and the local part of the heap, right? So if the local, there is no synchronization on it. So it's not surprising, but we do get that result. So we got the check mark on the single thread performance one. And we also measured a port of the NASA parallel benchmarks to Java and Ruby and compared it with Fortran and with Truffle Ruby. If you're wondering, those black lines are actually the theoretical upper bound. Just take the single thread performance and multiply by the number of threads. Now, this higher obviously means better here, and this basically is a scalability result, meaning it's the ratio between the performance of a specific environment versus its own single-threaded execution. So if you see, for example, if say Ruby is faster than Fortran, it doesn't mean that it's really necessarily faster. It just means that it scales better specifically for this case versus its own single-threaded performance. Now, this sort of benchmark is embarrassingly parallel, so it benefits from that shared fixed storage strategy that we talked about, and that's part of the reason why we can measure it with Truffle Ruby, which runs with the tightrope thing, right? Which has no synchronization, because we know that there is no contention, but in real applications, we wouldn't want to take that risk, all right? Yeah, we know there's no contention. So that's how here we do have the thread safety, but we also have the concurrency and scalability for that. About our choice of the lightweight layout lock, we did try other locks. We measured with other locks. We measured with the original layout lock. We measured with re-entered lock and stamped lock. And what we noticed is basically that layout lock and or the lightweight layout lock behave similarly or perform similarly when there are read and write accesses, because there's no contention between those thread states and they can do whatever they do. On the other hand, stamped lock and re-entered lock, they all have contend on a shared variable. They have this tendency to contend on a shared variable, and that's why they don't scale. They're sort of on the bottom there. On the other hand, we see on the right side that the layout lock is actually on the bottom here because it assumes layout changes are rare, so it will do a very heavy process for every layout change, while the rest of the locks, including the lightweight layout lock, perform well. So out of all these locks, only the lightweight layout lock performs well in both cases, right? So what we've seen is we showed how we synchronize built-in collections in dynamic languages using concurrent strategies. This concurrent strategies method, where we use the lightweight layout lock for the fully synchronized stage. No more lack of thread safety, so you can have your safety net now. And we did all of that. We answered all these requirements, and that's it.
Hello, this is Phil Pieslow. I work on JavaScript core. Thanks for citing my blog post, but maybe next time you can cite it a little bit better. Two problems with how you cited it. First, it doesn't require locking on every access. So that's very explicit in that blog post. Absolutely does not require locking on every access. Read and write accesses don't lock. Many layout changes don't lock as well. So achieving good single thread performance and scalability are explicit stated goals of that approach, like yours. I think the primary difference between your approach and our approach is that you use the style where there's transitive sharedness, whereas we try to avoid that style. And you guys have implemented it first. We're still thinking about it because we have a big VM, so it's really cool to see this in action. But you know, we're both working on the same thing, so maybe next time you can not claim that we're locking on every access, because that's just simply not what goes with.
All right.
Maybe I can answer this one.
Sure.
So sorry for that, and we are very happy you are here and you are right. In the paper, we do a more detailed relative work comparison with your work. Mostly, like I think for the array, it's not very clear in the blog post how it worked exactly. So there are still open questions, basically. I think it's like the different approaches, but very interesting, and it will be very interesting to see your work implemented and see how that would work out.
Yeah, I think when these approaches can be compared, it'll be super interesting, and there are trade-offs all over the place. So it's
exactly.
anybody's guess who lands closer to good single-thread performance. But saying that we're like throwing that out the window is not. It's just not accurate.
Yeah, I've just taken one aspect of it because I had to go really fast through that. So that's that, but for a specific case.
So I notice in your design, once you move something from one kind of memory to the other, the whole collection stays there. So at least for the cases, the benchmarks that you are considering, they have a pattern of locality of access. There are concurrent accesses, but other systems have gotten good performance out of a notion of slicing. So have you considered any such approaches?
Yeah, let me try to answer that. When we show the local part of the heap and the shared part of the heap, the distinction is abstract because the objects themselves do not move. We don't play with the memory management system. So if you allocate it in such a way and the benchmark already uses it in that form, it will still keep working that way. It's just the shape itself for the object is the one that changes, that tags the object as shared, and some of the methods like write accesses have a special access checks for the assumptions on them to make sure you don't violate the assumptions. But the objects actually stay where they are. So they don't yeah, you can disconnect that. The objects don't actually move around.
All right, it's time to speak one more time.